Good morning. Okay, so let's carry on from where we left last time. So we were looking at we had just started a discussion on these extended surfaces, and in the last class I mentioned what kind of fins we can actually see in practice. So today what I would do is I would set up a method to analyze the heat transfer processes in a fin, and then we'll use those to make some to take it further to look at how you know many of these heat exchange devices which have fins, such as these two that I've shown on this picture here, or on this panel here, how these two were actually designed. Okay, so I would not. We will do some problems in the tutorial which would go into details of the actual calculations. But what I will do today in the lecture is to just set up the mathematics or the treatment required to analyze these fins. So what we'll do is we'll start with a single fin. Okay, so this is I'll build up a general analysis, and then we can apply that to any fin geometry. We limit ourselves to simple fins. Some of the other geometry, especially I don't want to cover every single aspect in this lecture because this treatment can be very long. Some of the special geometries are actually their results are very clearly given in your book. So I would request you to refer to the book. There is a table there which lists down all the different quantities that I'm going to derive today. But I will limit myself to some very special geometries today, and you'll see what these geometries are. Uh, okay, so we'll start with the general energy balance. So the fin, a single fin would be something like this, and I've taken very specifically a fin which has a cross section area which is not uniform. Okay, and we'll use that idea because I want to build a theory for a non-uniform cross section fin. So you can see that as you go along the x direction, as you go along the x, the area of cross section across which conduction happens is actually decreasing. Remember that it is surrounded by a fluid, so the fluid heat transfer coefficient and the temperature is also something that we know already. That could be maybe ambient air or some heat exchange fluid that we employ. So we before I start my analysis, I would like to list down a few assumptions that we'll make in this analysis. And these assumptions are very critical in getting an analytical solution for the problem that we're going to work out. The first assumption that I would make is that this is a special case of 1D conduction only. Even though the geometry is two-dimensional, remember the fin is, as I've shown here, it's actually can be easily perceived to be two-dimensional, that temperature should vary both in x and y. But I will actually assume in this case that the conduction only happens along one direction. So the reason for that is that so when I said 1D conduction only, I would say temperature is only a function of x, and I'm making that case because I know that these fins are very thin structures. So if you look at these pictures again, these fins are very thin. So that is the y direction. The x is actually the length of the fin. So I would say that the gradient of temperature along x will actually be much more than the gradient of temperature along y, which would mean that the temperature across the y direction would be nearly constant, which I can assume. Okay, so this is true if the fin is thin. So I'm making this because the fin is a thin solid. The second assumption that I'll make would be that we will analyze these systems under steady state. So we don't look at the transient response, or we don't look at how heat transfer actually started from T0. The third I'll do is I will assume that the thermal conductivity of the fin is a constant. Fourth thing that I will assume is that radiation could be neglected, because that again makes the problem simple to analyze and simple to work out. Fifth is that inherently the fin has no heat generation. So we won't see any heat generation term in this fin. And the last assumption that I would make is that the heat transfer coefficient of the fluid, remember there's a fluid that's surrounding this fin, the heat transfer coefficient is constant over the surface. So it does not vary spatially. Okay, so, and that is a key assumption. As we'll see when we go into convection, this actually is not true, but for most design analysis, this is a good assumption to work with. And I'll tell you what are the caveats, or under what conditions can we assume this safely. So we will get to that at a later time in this lecture. Okay, so with these assumptions, let me also list down how we will do this analysis. I was saying the last assumption is h is constant over the surface. And so what we'll do is, I said we'll do a simple, also we'll analyze this problem at steady state, but very similar to what we've been doing, we'll apply the energy balance, okay, to calculate the temperature distribution in this fin, and then from the temperature distribution calculate the heat transfer rate that is going through this fin. So those are the things that we want to do, or we want to figure out. Now, what I was saying is that what we can do is, at a distance x in this as shown here, at a distance x from the base, this is what I was saying is the base. At a distance x, I take a small element which has a thickness dx. And as shown in the figure here, the cross section area is also a function of x, because the cross section area is actually decreasing. So the area through which the heat transfer is taking place is decreasing, very similar to that one problem that we did in the first tutorial sheet. Okay, so anyway, so you have qx coming in, qx plus dx going out. Okay, so qx plus dx is going out. That is because of conduction, but we also have the presence of a fluid surrounding this fin. So I can say that from this element, right, this small element that is there, we will also have some amount of heat transfer taking place because of convection. So I'm going to write this as dq convection. So this is dq convection from the exposed area. Then imagine this to be like a like a, maybe let me show you something. Yeah. So let's say this is the fin. This is actually a very good shape. This is a sanitizer that I'm using anyway. So you can imagine that this is this area, the surface area through which a small, the element is small. It's a small dx element there, small dx element, but through that area you have heat flow or heat transfer taking place to convection. So we need to account for that to be able to calculate or to be able to do a complete energy balance. So energy balance then dictates, remember we say that E dot in minus E dot out plus E dot generation is E dot storage. So there is no storage here because we are looking at steady state. There is no generation because I said Q dot is 0. So clearly E dot in must be equal to E dot out in that element. So E dot in is Qx and E dot out is Qx plus dx plus dq convection. I hope that is clear. Okay, these are the only things taking place in this system right now. Okay, now what is qx? Qx could be written using Fourier's law. This is minus k ac dt dx, and so that means qx plus dx can be written as in the form of a Taylor series again. So that would be qx plus dqx dx into dx. So I can write this as minus k ac dt dx minus d by dx of k ac dt dx dx. Now that is qx plus dx. What about dq convection? So dq convection would be because of heat exchange, because of, or we can quantify dq convection from Newton's law of cooling. So we can say this is going to be h times T minus T infinity. Remember, T is the local temperature of that element. Okay, T as a function of x into the area, surface area, which is dAs. Now, this is when I say dAs, that is the surface area. As I was saying, that would be, so the surface area would be something like this area, and it also goes behind, maybe something like that. So that would be the surface area through which this heat transfer is taking place. Okay, so surface area is not the same as cross section area. Please keep that in mind. Okay, let's not make a mistake there. So this is dq convection. So what I can do now is substitute these back into the conservation equation, and then we can simplify. So what we get is minus KAC dt dx would be again minus KAC dt dx minus, now K is constant, so I will pull it out and just write this as d by dx of AC dt dx plus H DAS t minus t infinity. So some things cancel off, this goes away. And so we can write this as d by dx of AC dt dx minus H by K DAS t minus t infinity to be 0. And if you want to take it one step further, you can write this second order ODE to be d2t dx square plus 1 by AC DAC dx dt dx minus H by K AC DAS dx. Oh, I'm missing a dx somewhere. Sorry. Yeah, it should be here. Sorry. If I divide the whole thing by dx. So DAS dx into t minus t infinity is 0. So that is what would be the differential equation that governs transport in a fin or in an extended surface. And this is a general equation, because remember we are we're looking at scenarios where the cross section area can change as a function of x. So it need not be specifically fins where the cross section area need not change. So but what I'll do is, in this lecture I will not focus on those situations where the cross section area is a function of x, because the analytical solution to those problems is difficult. Okay, and it is there in the book. I don't want to go in and try and spend time hours trying to derive those. I would rather look at some simple cases which are frankly which I can address for these two kind of scenarios. Okay, these two scenarios are fins where the cross section area is nearly the same, okay, all through the fin. So I will address these kinds of problems. So to do this, I will consider only fins of uniform cross section, and these are typically rectangular fins or pin fins. So what I mean by that is, if you go back to what we did in the last lecture, we had one image somewhere, I remember. Oh yeah, there it is. Okay, so we will look at, in this analysis, I will specifically look at first case, okay, which is a rectangular fin of uniform cross section, and I will also look at pin fin, but with a uniform cross section area. So I will look at a fin which has something like that as a shape. The area remains the same. Cross section area remains the same. Okay. So in either case, in this case, for instance, in the case of rectangular fin, the area of cross section is just width times the thickness, and in the case of pin fin, the area of cross section would be pi d square by 4, where d is the diameter. And we look at another variable in the problem which I should have defined earlier, but we also look at the length of the fin. L, which is the length of the fin, will also be a parameter in our analysis. Okay. So now remember that if I'm dealing with these two scenarios, DAC dx is actually going to be 0, because the cross section area is not a function of x, and that is the main reason I'm saying we will focus only on these kinds of geometries, so that I can get rid of this term in the differential equation. Okay, so dAc dx is 0, which means now the governing equation becomes d2t dx square minus h by KAC DAS dx into t minus t infinity to be 0. Now, interestingly, DAS dx is actually, if you think over it, this parameter is the perimeter of the fin. Because you have to see that the perimeter times the length, some distance x is what is AS. So DAS dx becomes just the perimeter. So I will denote the perimeter by parameter P. Okay. So we can write this as d2t, or before I write that, let me also make one more suggestion. Because I'm trying to solve a differential equation in which t is a parameter, and then I have this t minus t infinity sitting here, when t infinity being a constant, I will define a new temperature, or which I call as excess temperature, which is theta, which will be t minus t infinity. So I will measure all my temperatures against T infinity. So, and that doesn't make any, I mean, that doesn't, it's not going to make any difference to the calculation. It just helps me because I can then replace, I can say d2 theta dt square or dx square would be d2t dx square. So the second derivative does not change. So what it does is I can now write d2 theta dx square minus h p by KAC times theta to be 0. That becomes my governing equation. And typically in heat transfer calculations, this, or not just heat transfer, even general physics, such equations are written in the form where this coefficient is written as some number square. So I'm going to say it as m square, hp by kc. And the reason for writing that is, I hope you have done this in, I think, the first year mathematics courses, the differential equation course, that now I can solve this equation, which is d2 theta dx square minus m square theta, quite easily, because I know the general solution to this equation is in the form of, I mean, I hope you have seen this equation, but the general solution would be some coefficient c1 times e to the power mx plus c2 e to the power minus mx. That would be the general, am I saying general equation? I should say general solution. So that would be the general solution to this problem. Interestingly, if you had this to be a positive sign, then you get an equation for a simple harmonic motion where then the solutions become cosine and sine, which we'll also look at very shortly now. In another problem, we'll also work with that equation. Okay, so we have two constants here, C1 and C2, and we need to determine C1, C2 using two boundary conditions. So the first boundary condition that we typically enforce in all fins, which is a common boundary condition for irrespective of the geometry or the shape, we specify theta at x equal to 0. Remember, x equal to 0 is starting from the base, where the fin starts from the base surface. So theta at x equal to 0 is sometimes given in terms of a base temperature, which we know. So we can write this as Tb minus T infinity, where Tb is the base temperature. This is the temperature at the base, which I can also write as theta b, as a new variable theta b, which is known, because Tb is known, T infinity is known. So at x equal to 0, that is a temperature which should be equal to C1 plus C2 from the boundary condition, I mean, from the solution itself. So that would be the first boundary condition to determine these constants C1 and C2. Now, the second boundary condition comes from the tip, the far tip, right? We start at x equal to 0, which is here. We are starting at, let me also say this we're starting at x equal to 0 here, we need a boundary condition at L, at the end of the fin. Now there are four possibilities to commonly taken, and I will cover each one of them in, depending on how important they are in a certain amount of detail, or I may just skip them. But let me introduce these four types of boundary conditions at the tip. So boundary conditions at the tip, and one of these is what we will typically use depending on what is given, what conditions are given. So the first case, or the first type of boundary condition, is that if we say that, let's say the fin was very, very long, so L maybe goes to infinity. So it's a long fin, which means L is going to infinity. So what should happen to that end? If you look at this sketch again, let's just think about this. If the fin was very, very long, so a long fin means that what do we expect at this point is the question, that what should be the boundary condition at this end at x equal to L. Now you can think about this, that if the fin is very long, then it gets sufficient time for the solid to cool down to the surrounding fluid temperature. Okay, so in which case theta at x equal to L, where L is tending to infinity, is goes to 0, because theta is defined as t minus t infinity. So t is basically going to t infinity, so theta should go to 0. So that would be if the fin is very, very far away, so it gets sufficient distance to be able to cool down to the surrounding fluid. Now if theta L goes to 0, and I know that L is going to infinity, and my solution has these exponential terms, clearly C1 has to be 0 for the solution to be bounded, because otherwise this will go to infinity. M is a constant, is a positive number. So that means C1 would be 0 in that case. And so I can write that theta straight away would be theta b times e to the power minus mx as the solution to the problem. And I can then write, I need something which is more than the temperature. So what I'm really interested in from the fin is to find out what is the rate of heat transfer going through this fin. So I'm trying to find out what is the rate of heat transfer at the base. So how much heat is being transported out of this fin? Because if the fin was not there, that it would have been heat transfer from the base itself, from a solid, from a flat surface. My concern is to calculate what would be QF, because QF dictates sort of my design, whether I actually need benefit by using a fin, or whether I'm losing something by using this fin. So QF is heat transfer rate at the base, and I would use this terminology throughout. Now QF doesn't mean it's a heat transfer to the fin, it's just that it's a fin heat transfer rate, how much heat is being taken away by the fin. And so basically whatever is being given away is actually coming from somewhere. So this is what we started with, and eventually the fin will actually dissipate or give away all this heat to the surroundings. So QF should actually be minus K AC dt dx at x equal to 0. That is what is the number one priority for me right now in design of any fin, or any heat exchanger which is employing fins. So this comes out to be square root HP KAC into theta B. So that is a heat transfer rate taking place through the fin. So this is a simple case, and I wanted to start with this because this is the simplest way of understanding how a fin might be working. What kind of temperature distributions do we expect? Now there are more complicated cases. The second case is if the fin tip is insulated. If the tip has some insulation on it, so you cannot have any more heat transfer taking place from the tip, which would mean that d theta dx at x equal to L is 0. Remember, there's conduction. Insulated tip would mean that the conduction flux is 0. So if you use this condition with the solution, and these are steps that I'm going to skip, and I'm asking you to please derive them on your own. This is the condition. If you use, you can then derive that the solution theta by theta b will come out to be a ratio of two hyperbolic functions. So cosine hyperbolic of m times L minus x by cosine hyperbolic of ml. Okay, this is ml minus x. And secondly, the heat transfer rate, which we can again calculate using the gradient of this function, would be square root hp kac times theta b times tan hyperbolic of ml. So that is the heat transfer rate if the tip was insulated. The third type, which I don't like actually, but your books, whichever book you pick up, would actually have this boundary condition as well. The third type is when you somehow know the fin tip temperature. So tip temperature is known, but this is rarely the case, and so I don't prefer this. But I'm just saying this for information only. I'm not going to work out the answer for this. So tip temperature is known would mean theta at L, which could be written as, let's say, TL minus T infinity is given. So you can then write this as C1 e to the power ml plus C2 e to the power minus ml. And now you have two equations in C1 and C2. So you can calculate what would be the solution profile. And I'm not going to do that. As I said, I don't think this is a realistic condition. So I'm going to skip this for the purpose of this lecture. The fourth is actually the most realistic. The most realistic one is, you can now imagine what we may have on the fourth one. So we looked at a long fin, we looked at an insulated tip, we also said that they're somehow known at this tip. The last thing that we are left with is that the heat transfer at this surface happens through convection. So whatever conduction flux comes in, that is taken away in the form of convection. So basically we have the mode changes at this surface. We have from conduction to convection. So the heat transfer mode shifts. So we can say minus K AC. And now remember, I'm dealing with constant area cross sections. So I'm writing AC very generally, very loosely, but I mean that AC is constant. dt dx at x equal to L, this would be the heat transfer rate because of conduction in the right towards the right. This should be equal to HAC. So at the tip, we have conduction flux, rate of heat transfer changing modes. So minus KAC dt dx at x equal to L should be HAC. Remember, it's heat transfer now taking place through the cross section, not through the surface. Be careful about this. Into T minus, or I should say T at x equal to L. So this is T. I don't know how should I, yeah, T at x equal to L minus T infinity. And knowing that dt dx is the same as d theta dx, I can also write this as minus K d theta dx at x equal to L to be H times, let's say, theta L. Where AC is cancelled because it's the same factor on both sides. So then we can solve this equation. Again, I'm leaving this to you, but the solution I can put up here because that is something which is important. So theta by theta b will come out to be cosine hyperbolic of m times L minus x plus h by mk sine hyperbolic of m times L minus x divided by the cosine hyperbolic of ml plus h by mk sine hyperbolic ml. Now, just to give you a physical insight on what is taking place in the fin, if we plot the temperature variation, let's say in the fin, so we plot theta versus, let's say, x, okay, and we have maybe L somewhere, and this is starting from 0, and we have maybe theta b as the maximum temperature. So what you will see, if you plot this function, you should be able to get a profile which goes like this, a profile that is gradually decreasing. So the special thing about this profile is that d theta dx is actually decreasing with x. Now this is somewhere where I want to spend a minute, and I want to see whether you've understood why this is taking place before I move on. So can somebody tell me, or can somebody guess, why is d theta dx decreasing? Anything that you feel can give us some insight into why this should be taking place or why this should be happening?
There is convection happening from the surface area. As we move further in the x direction towards L, the heat, more heat will be getting transferred from convection. So the conduction heat transfer rate will be low, and so the heat difference will be getting lower as we move further.
That's very good. So actually, it's a very good point. It's that's precisely the answer. Actually, what is taking place is, you think of it this way: that you're starting with maybe a glass of water, okay, and I can say the quantity of water there is, you can sort of say it's analogous to the amount of heat you can transfer. As you go along, maybe the water is getting sipped away. Somebody puts a straw and sips away continuously. So by the time you reach the end, the amount of water that you have left to transport is actually decreasing. Same thing is taking place here, that you have start with the conduction flux, and because of convection there is this transport of heat. So heat is being taken away gradually all over the surface. So the conduction flux will keep decreasing as you keep going down, as you keep going along the length, and that is precisely that is taking place. D theta dx is decreasing. That means heat transfer because of conduction is actually now decreasing as it goes further. Okay, so there is heat loss because of convection, and that is precisely the reason why we have designed this fin. We want to have higher area, and we want to dissipate heat into the surrounding fluid as effectively as possible. Now, similar to the earlier cases, we can also write the total heat transfer from the fin. So this would be again minus k ac dt dx at x equal to 0. And so you can take a derivative and substitute those values, and so you should get this to be square root hp kc times theta b times sine hyperbolic ml plus h by mk cosine hyperbolic ml by cosine hyperbolic ml plus h by mk sine hyperbolic ml. Now, if you notice, this expression is far more tedious as compared to the earlier ones that we've derived. And I'll put this back again so that if you want somebody's writing, at least they can note it down. But this expression is far more tedious than the ones that we have already derived. And so what is typically done is, instead of calculating so many numbers and substituting again and again and getting this number, an approximate method is used to calculate heat transfer rate in the case of this convection boundary condition. Okay, so we use an approximate solution for the heat transfer, and this approximate heat solution is based on using the result from the insulated tip case. So we use the solution from the insulated tip case, and we just replace the length there, the length that was coming in, we replace that by sort of like a corrected length. So this corrected length is the actual length plus some correction which happens because of the tip area by the perimeter. So this correction, or if you want to interpret, so let me show you graphically what is going to happen. So graphically, what I'm saying is if the fin was, let's say, this long, okay, its length was L, and there was convection taking place from the surface and the tip, then what we are now replacing this with is a new length. Maybe I'll draw it here right below it to make it more clear. We are replacing that with a new length, okay, where the tip is now insulated. And so this additional length that we have included, this length is given by this equation. And why does it come out like this? So the interpretation is that if you multiply both sides by P, you will get PLC will actually become the corrected area. So that is the corrected area through which heat transfer takes place. P into L is actually anyway the fin area, so the lateral area. P into L will become the lateral area of the fin plus the tip area. So we are sort of incorporating this length here, which sort of transforms this straight section into sort of, you can say that the equivalent area is transferred to the lateral section. Okay, equivalent area, not the equivalent length, but the equivalent area is moved to the lateral section, and then we can say that the tip is insulated. So this method, then what it allows us to do is that this length LC can then be used in the insulated fin tip case, so which was case number 2. So now I can write that the heat transfer rate can be used or can be calculated from this equation itself, except L will actually be LC. So this is a smaller expression to calculate instead of doing this much longer calculation, and it tends to give fairly accurate results. This you don't lose, you maybe you incur an inaccuracy of about 1 or 2%, not more than that. So this is always something that can be done. If you're doing a computer calculation, then of course we can do the more rigorous method. But sometimes when you're doing in an exam, or you want to have a quick estimate, this could actually be one way of calculating things. Just to again illustrate what kind of corrected lengths you will get. So for example, if you have a rectangular fin, in which case the perimeter is, let's say, 2 times W plus T, because this will be the width into the plane and T, which is the thickness. If you see let me show this picture again. Yeah, so you see this picture. So the perimeter would be W T plus W plus T, so that becomes 2 times W plus T. Okay. Or if you look at a straight fin of this type, pin fin, then basically you have the perimeter becomes just the circumference, which is pi into d. So for rectangular fin, P is 2W plus T, and typically these fins are made in such a way that the thickness is much smaller as compared to the width. So this is approximately 2W only. These are thin fins, and I'll talk to you about very soon about why this is thin. So 2W is sort of the perimeter. So that means that LC will be A plus the perimeter, the area on the tip, which is W times T, by 2W, which is the perimeter. So that becomes L plus T by 2. That sort of becomes the corrected length for a rectangular fin. You can prove that for a pin fin of uniform cross section area, the corrected length will be L plus D by 4. And that's simple because the tip area is pi d square by 4, perimeter is pi d, so you get d by 4 there. Okay, so we can always use these kinds of corrections to get quick estimates. Okay. So now let me talk about something which is more fundamental than just maths. So far we only looked at maths and how do we get temperature distribution or heat transfer rate from a fin. The more fundamental aspect is that there is no guarantee that putting a fin on a device or on a heat exchanger will actually give you a better performance. Okay, so there is this issue of economy versus so how much cost you incur versus how much you gain in terms of heat transfer rates. So, and the reason for why having a fin may not be beneficial at all, it may actually be worse, is that this fin is actually made of a material which is a conductor, but it inherently offers its in itself it offers conduction resistance. If the fin material had no conduction resistance, that would have been the best possible solution. Then you have all the heat just straight away it moves out. But that is not the case. A fin offers conduction resistance, so that there's an interplay between conduction resistance and how much you are conducting away because of convection. So what we'll do is we'll define two fin performance parameters. So let me say fin performance parameters. One will be what we'll call as effectiveness, and the second would be fin efficiency. So we'll use two parameters to quantify fin effectiveness or rather fin performance, and let's begin with each of them and see how they're different and what do they bring in to the table. What details do they bring about the fin design. So effectiveness is actually defined in terms of, or effectiveness is given by a symbol epsilon f, and this is sort of it's a ratio of heat transfer rates. It's a ratio of the fin heat transfer rate, which we are already calculating qf, fin heat transfer rate, versus what heat transfer would have happened if there was no fin employed. So heat transfer rate, let me say without the fin. And this is a purely hypothetical comparison, because typically you would actually design a fin, use it there, and then you're sort of now backtracking to a scenario where there was no fin. So what would have been the heat transfer rate if the fin was not there? Okay, so it's a hypothetical comparison. Keep this in mind. And so to write in terms of mathematical numbers, epsilon f becomes qf by what would be heat transfer rate without fin. That would be h times area of the cross section at the base, ACB. I'm going to write area of the cross section at the base times theta b, because theta b, I mean, remember that if there was no fin, you will have temperature difference from TB to T infinity. So we are saying if there was no fin, this would be the temperature change. ACB is the area of the cross section at the base. ACB is area of the cross section at the base of the fin. So we look at a ratio of these two numbers. Now, typically fins are supposed to be effective, or they're called effective, if epsilon f is greater than or equal to 2. If it's less than 2, then we don't consider that to be an effective design or a fruitful design. That is actually comes under the category of those bad designs which should not be followed. Now, one of the things that you need to remember is that even though I'm defining this effectiveness in this manner, I have considered that h, I very loosely use that h is constant. Even without the fin, I have said that h is still the same. It's still the same fluid, still the same heat transfer coefficient. But actually, it is uh, it is an assumption that we have to deal with. There is no other option for us. If we start looking at fluid, because remember, h depends on the flow velocity, and so if you have an obstacle in the flow, then definitely there will be a boundary layer, and so h will change. And without that obstacle, which is the fin, h value will be something else. but we are neglecting that variation as of now. Okay, for this, purely for this analytical treatment. If you want, if in industry, if you, let's say you're doing this kind of analysis, you will actually go into much more detailed, maybe numerical simulations to calculate the heat transfer rate, so you will not take H to be constant. You can actually solve the, momentum equation, the Navier-Stokes and the energy equation, to determine what would be H at that point. But we are doing this purely, using analytical methods. So there we have to deal with H to be constant. So remember this, that there's a shortcoming of this method that I'm showing. So to show you what effectiveness looks like, let's just look at hypothetically the scenario of an infinitely long fin. So let's consider an infinitely long fin, in which case we said Qf was square root HP KAC theta b, and we're saying long fin, we are sort of saying long fin with uniform cross section, because we developed these equations for only a uniform cross section fin. So in this case, epsilon f becomes a ratio of HP KAC theta b by HAC theta b. So theta b cancels, and now I can write this as square root K P by HAC. That becomes the effectiveness for an infinitely long fin. Now, what does this tell us? And there's a reason why I'm doing this. What does this equation tell us about the effectiveness? One thing it tells us is that clearly epsilon f will be high if the conductivity is high, and this is the conductivity of the fin material. So this tells us to use high conductivity materials, which are typically copper or aluminum. So that will explain, when you look at these fins in the problems that, or the scenarios that I discussed today and even in the last lecture, everywhere you would see copper fins and aluminum fins. And in fact, if you go, if you end up buying an air conditioning system, of your own, or if you go with your parents or someone, in trying to see what they're buying, you will see that typically companies will say that their fins, it's an aluminum, or it's a copper fin system, that, for better heat exchange, so that allows more amount of heat rejection, and so it decreases, rather it increases the coefficient of performance of the air conditioner. So you see that why these are important, just because from these basic calculations, that conductivity can, if high conductivity would mean effectiveness will be high. Similarly, effectiveness will be high if we have the ratio of P by AC to be large, because see, epsilon f goes as square root of P by AC. Now you may work this out and see that in the case of a, let's say in the case of a rectangular fin, AC you know uh, is W times T, width into thickness, and perimeter I said is like 2 times W. So clearly P by AC becomes like 1 by thickness. So that means that if thickness is small, the ratio P by AC becomes large, and so effectiveness becomes large. So we need thin and closely packed fins. Thin fins will justify a high effectiveness, but they should not be so thin, or rather, no, they should not be so closely packed. Having them very closely packed would mean that there would be obstruction to flow of the fluid, the surrounding fluid, and then that brings in fluid mechanics, considerations, growth of a boundary layer, which impedes heat transfer. So it should not be. So there are these competing objectives that you have to meet. You cannot make it very close, but you should have it sufficiently close to allow heat transfer to take place without reduction in the heat transfer coefficient. Finally, epsilon f will actually be high, I should say, if H was low. Now this sounds very strange, but And I'll tell you why I'm saying this. I mean, we definitely don't want a fluid which has a low heat transfer coefficient. But still, it seems that if H is small, then putting a fin will make it more effective. Now, why does it happen? So it basically happens because when you use, or in context, let me put this in context of what you see around you. Typically, fins are used on the gas side. Fins are never used on the fluid side, and the reason is for this. From this calculation, we can see that if you put for a liquid side, effectiveness will actually become low because H is very high. On the gas side, if you remember from the first lecture when I listed down some heat transfer coefficients for gas, for liquids, both in natural and in forced convection. I said H is much smaller in free convection, and also it's much smaller in gases. So it makes more sense to put fins when you're dealing on the gas side instead of on the liquid side. So if you look at the car radiator, these fins are put on the outer surface where heat exchange has to be to the surrounding air. Similarly, with the case of an engine block or heat transfer from taking place from a microprocessor or air conditioner, these fins are always employed on the air side, on the gas side, never on the fluid side because it is more effective there. So the inference that I'm drawing here is that you need to use fins, or fins work best on the gas side, especially especially if there is free convection is the only mode. So if you do not have the liberty, or if you do not have the freedom of putting a blower there, then if you have free convection and you are on the, of course, on the fluid, on the gas side, then it would make more sense to use fins there instead of putting it on the liquid side. Liquid side will not actually need a fin because the H value is already so high. Okay. Okay, so let's look at one more basic calculation here. Let's also look at the definition of fin effectiveness, but instead of writing it in terms of the way I've written it here, I've written it in terms of heat transfer rates. We can also write fin effectiveness in terms of resistances, thermal resistances. So I can say that epsilon F, which was Qf by H theta B, let's say ACB, I see that on the base, H 1 by H ACB is sort of like the resistance to convection from the base. So I would say RTB. Okay, 1 by H ACB is the resistance to convection at the base if the fin was not there, of course. And I know that theta B by QF. QF is the actual flow, actual heat transfer rate. Theta B is the potential difference, the difference in temperature across which total heat transfer is taking place. So this should be R, let's say, thermal resistance because of the fin, RTF. So I can say that the effectiveness becomes a ratio of RTB and RTF. So the effectiveness is a ratio of the resistance to heat transfer from the base, that is convection, by the way. RTB is only because of convection, and RTF is the resistance to heat transfer because of combined conduction and convection. It is not just one, because the fin is actually taking away heat both in the form of conduction and then it convects. So it is a combined resistance. So clearly, for a fin to be effective, we want RTF, the fin resistance, to be smaller, ideally much smaller, but smaller than the base resistance. If that is not the case, then we should not be using a fin. Okay, so that is the fin effectiveness. The last fin performance parameter, as I mentioned, was efficiency. So fin efficiency, I should say. Now, this is also this is actually a concept that is very similar to what we do in thermodynamics. Okay, we look at its efficiency, so it must be less than one. So we look at what actually happens versus what could ideally happen. So this sort of compares the actual heat transfer rate to the rate of heat transfer if the fin offered zero conduction resistance. So this compares the actual heat transfer rate to an ideal scenario, which is ideal scenario is when the fin uh, had no conduction resistance, which would mean that the fin material had an conductivity which is infinitely large. So I can write fin efficiency, which is a parameter eta f. So eta f is written as the actual heat transfer rate, which is Qf, versus a case where we had no conduction resistance. That would mean that the maximum heat transfer, so let's say Qf max. And what is Qf max? So if there was no conduction resistance, you can imagine that the whole fin would be at the base temperature because there's no conduction resistance. So we can write the Qf max to be h times the area of the fin times theta b. And think about this. If you're not convinced, think that if there is no conduction resistance, the base temperature should propagate throughout the fin because there's no potential, there's no drop, there's no resistance, so there's no potential drop. Similar to electrical circuits, I keep using that terminology very often. So there is no potential drop. That means there would be that the potential remains the same throughout the fin. That means theta b remains throughout, but then that theta b heat transfer takes place through that entire theta b to to zero temperature, because zero would mean that it's theta is zero there because it's t minus t infinity. So in this case, also we can do a quick calculation. Let's say we have a straight fin with a uniform cross section, and say we have an adiabatic tip. Or that is the condition that is given, that the end is insulated, the tip is insulated. So we can write eta f in this case to be square root hp kac times theta b times tan hyperbolic ml. Remember, there was this tan hyperbolic function in this particular solution, divided by haf theta b. Now, what is the fin heat transfer area? So in the case of an insulated tip, the fin heat transfer area is actually the lateral area, okay, or the not the tip area, but only the area which is in the lateral sense. So AF will actually be the perimeter times the length. The perimeter times the length of the fin would actually be the fin heat transfer area. So if you put these values in and then simplify, right? So let me do this here. HPKAC square root into theta b anyway gets cancelled here. So let's just get rid of this. And we'll have tan hyperbolic of ml by HPL. I hope I'm not missing anything now. So square root HP will actually give me square root KAC by square. So this will be KAC by square root HP into tan hyperbolic ml by L. But then I know that HP by KAC is actually m square. So this becomes tan hyperbolic ml by ml. By the way, you should note that the units of m are inverse length square root, meter to the power minus half, length to the power minus half. its inverse length, not square root of inverse length. Okay. So what is special about this now? The reason I wrote this is because if you look at this number, this is the case where I can look at the limits of this number. So if ml, let's say, was to go to 0, if this product was going to 0, you can actually prove that this eta f will actually go to 1. So this product will, if it's becomes sufficiently small, eta f approaches 1, and if ml goes to, let's say, infinity, then this eta f value goes to 0. So it means that if I just look at the first case itself, if ml goes to 0, it's quite understandable to see that the fin will be very effective because there would be no conduction resistance encountered. There's no fin, basically. So that's great. That is basically giving you highest efficiency. But then the effectiveness is not there. So the reason for defining two parameters is sort of like this: that each parameter does not capture the true essence of the fin. So each can be misleading in its own right. For instance, this efficiency tells me that ml should be 0, so that sort of like length should be 0. But then it does not give me the kind of heat transfer I want. So because this is comparing it to an ideal scenario. Effectiveness deals with hypothetical scenario that if the fin was not there, how much were you actually getting? And so how much are we gaining over and above that? So we use these two parameters, to define fin effectiveness, and that's how engineering judgments are made. Okay, we want something which has a high efficiency but also has a high effectiveness, and so some kind of optimization has to be done when such fins are designed, because both cannot be increased together. One increases and the other one may actually decrease. So we have to come up with some sweet spot where both can be increased to a reasonable level. Okay, so I'll stop it here for today. I know I've covered a lot of material. Okay, thank you.